Well, good morning, everyone. It's 9:46. I think I'm going to start. Thanks for tuning in. I'm Mabby Amouie. I'm the Senior Director of Analytics and Chief Data Scientist for Norfolk Southern. I'm in charge of the enterprise-wide AI and data science initiative at Norfolk Southern. Last year, I had a more detailed presentation about one of our deep learning models and how we optimize it using techniques like AMP, XLA, batch inferences. To kind of put it on steroid in TensorFlow and have a large scale parallel inference. And this year, I kind of decided to dial it back and talk about another application of deep learning in our space, but on a higher level, and show and emphasize how important AI and data science has become in our everyday work. And I'm hoping that you'll find it interesting. It's a lot of material to cover within 20 minutes, but I'll do my best. So the presentation I have for you today is about accurate geospatial feature baselining using AI and LiDAR. I'm going to break it apart so that it's more comprehensible for you all about what even the geospatial features are and what we are doing in this space with LiDAR and AI. I'm going to start by giving you a little bit of background about Norfolk Southern, who we are and what we do, and talk about geospatial feature baselining. I'm going to talk about conventional surveys versus LiDAR and have a 2-second overview of what LiDAR even is, and also talk about how we automated everything using deep learning. So background about Norfolk Southern. We are one of the few largest railroads in the United States. We operate on the whole east of United States. One thing that's less known to a lot of people is that we own actually and operate many of our tracks. We own over 19,000 miles of track. Everything is owned and managed and maintained by us. And we basically carry anything from finished goods all the way to raw materials. You can think about any kind of appliances, toilet papers, tanks, military equipment, UPS packages, and all the way, as I said, up to raw materials like grain and lumber and whatnot. Basically, anything that goes pretty much long distance, it gets hauled by train. And again, as we operate on the east of the United States, we pretty much handle most of the goods going in that direction. Here's our operating map. You can see how it encompasses pretty much everywhere on the east side, and it's a pretty large and extensive territory. And then it kind of segues as to why we need a very accurate map for our features. And I talk about what even the features are. So geospatial feature baselining, let me talk to you a little bit about that. So let's talk about the vehicle space. Everybody puts, the direction of somewhere in their iOS map or Google map and Waze or whatever you call it. And these conventional maps, they have a very precise location of traffic lights, intersections, etc. And all these are the ones that we are calling geospatial feature. They have a very accurate location, which is what constitutes a map. In the railroad space, however, we don't have traffic lights like you have. We have signals, and we don't necessarily have things like intersections in the same way. We have railroad crossings, we have diamonds, we have all these different various features. We have switches that helps us go from one track to another. Again, from the overview perspective, it's pretty similar to what it is in the car space, and you can think about why it's important for us to also have a precise location of everything, especially as more and more we are moving towards automation with like self-driving cars. Having an accurate map helps it a lot. Companies like Waymo are all map-based to a great extent. And, when you talk about the railroad space, a lot of our automation projects are now more and more relying on the precise location of all these assets, which is why it's so important for us to have an accurate map of those things. Here's an example of a switch on the right side. In the bottom, you can see a switch is a mechanism that helps you to change track from one to another one. You are probably familiar with the railroad crossing on the top. Probably all of us have waited on one of those until the train passes by. Again, locations of these switches, crossings, they're very important for us. And you might ask yourself, well, how have you guys been operating if you don't even know the precise locations of these things? Well, the fact of the matter is that we do know the location of all these features, and we have a database for it. But the database was created a long time ago, and back in the day, the GPS technology wasn't as advanced as today. So there are some discrepancies, some precision errors in the database that we had, but good enough for our operating needs, but maybe not necessarily good enough for some of the automation. And as we talk about the autonomous trains of the future, maybe not so good about that. So the challenges that we had is the first one was that some of the data is outdated because of the, again, outdated GPS technology. So we need to update that. The second thing is that anytime you make a physical change to an asset, imagine you go and rebuild this intersection or move this traffic light from here to somewhere else. Well, somebody needs to track that. Somebody needs to go and accurately get the location of the new feature and go and update it in a database. All of it is manual. It's a very time-intensive process. It also relies on human. And anytime you rely on human, there's got to be some human error, right? So, which is why we have some challenges in this space. And I'm going to talk to you about how we've been handling all these challenges to date and how we're handling it going forward, ever since a few months ago when we rolled out these models. So I'm going to talk about conventional surveys versus LiDAR. And conventional survey is what you would use to map all these features in old days, or even right now for a lot of people. So essentially what it is that you see that guy on the right. So somebody would go to the feature, a switch, a crossing, a traffic light, a signal, whatever you want to call it, with an instrument that has a GPS capability and have to sit there for a few seconds, get the GPS location, and go manually update it in the database. So as you can imagine, it's a very time-intensive, labor-intensive procedure. And we call it baselining because it's basically building that version 0 of the map, right? You go and you find the features that you have, all these, traffic lights and whatnot. You get the locations and you call it version 0. We call it baselining that feature. You build the map, and going forward, what we call it, you change manage it. Anytime you make a change to the physical asset, you go and update it in the database and you track it, you re-GPS it. Now, what I didn't mention up to now is that on Norfolk Southern's railroad, because of how extensive that our operating territory is, we have 200,000 plus features. And that is a lot of features for human to have to go and manually track and manually update the database. So it's a lot of work. And again, as I said, it requires boots on the ground. Somebody needs to be in person, physically buy that feature, get an instrument, and try to map that feature, get its precise location. Very time-intensive procedure. Now let's see how LiDAR is changing that. First of all, what's LiDAR? You see there is a device on the top of this car. And this LiDAR device, in layman's terms, it shoots many lasers to the surrounding environment and gets responses back from those lasers. And based on some time of flight, it can accurately calculate the distance of any point that was shot at to the distance of the LiDAR device itself. So it ultimately gives us that, like the picture that you have, it's a 3D point cloud for every point, and it kind of maps the surrounding. For every point you have a precise distance of it to that particular car that you have. Now, what we did, we even augmented this with a precise GPS location using real-time kinematics. I'm not going to dig into that. And then basically for every point that this LiDAR is giving us, we not only have the distance of it to that LiDAR device, we also have a precise GPS location of it. So you can think about that as you're moving at 60 miles per hour, you're collecting this 3D point cloud of data, just like your self-driving car would. And for every point, you have a GPS location, so you can have it on demand at any given point of time. So we mounted this on the top of our car. You can see these are the cars that can go on the rail. They can go up to 60 miles per hour. And we mounted this LiDAR device on the top of it. It gives us 700,000 points per second at 60 miles per hour without the need of somebody stopping and, getting a GPS device and trying to, find the location of a feature. Now, the question is that you're collecting all this LiDAR data. How does it look and how are you using it? I'm going to show you some examples of it. On the left side, this is one of our yards or sorting facilities. You can see how rich the data is. I should say that we are presenting this in this presentation as a 2D image, but in fact, it's a 3D point cloud. So in software, you can navigate around it and see like the 3D surroundings. On the right side, ironically, you're looking at the railroad crossing. So here you see actually a vehicle stopping by. Here is another vehicle, and this is a railroad crossing, and you can see how perfectly you can see every detail about it. Now, you're collecting this data at 60 miles per hour. How are you using it? So here's where we changed the old traditional method of boots on the ground, somebody with an instrument getting getting GPS locations. We're collecting this data at 60 miles per hour. Everything is automatically capturing 3D point cloud with precise location of every point. Now, an analyst can go and say, okay, well, here's a railroad switch that I see, and I can just click this point and get its GPS location and update it in the database. So what does that mean for us? That means that you're no longer having to be physically on the track by that feature and getting its precise location. You can just be in the back office, sitting by your computer and, click on a point and get the precise location. And you can even compare it with what you had in old days in the database. So if I just show you guys, that's the point that we had in our database. Again, old GPS technology. Now that's as precise. So an analyst can go and say, well, that's kind of far, and that's not the accurate point. And I'm just going to click on this point and just get its GPS location and update it. Well, cool. But where's the data science in any of these things? You're introducing some automation, but you still are expecting an analyst to sit by their computer and go through 200,000 features on our network and click on every point and be able to get their your location. Again, you still have the human in the loop, right? And you still have the human that can generate human error in the process. And so again, it's a very heavily manual process if we just stop here. So we were like, okay, so what if we create a deep learning model that does what the human's gonna do? And like Andrew Ng always says, anything that can be looked at and have some inference by a human within 2 seconds, you should be able to do the same thing with deep learning. And this is what we did here. Pretty interesting, and I'm going to show you some of the results of the deep learning, and I'll tell you what we did. So we took this to the next level by using deep learning to automate what the analyst was doing, which is pick a point that corresponds to a switch, pick a point that corresponds to a crossing, or all these different traffic lights and features. So we got a very rich, very good sample of our LiDAR data. And we have this GPU cluster. So we created a deep learning based detector in PyTorch where we basically told, here are the points that we want to detect. And here's as precise as you need to be about them. And we, of course, did all the tuning and testing. Really, the output of this step was a deep learning model that would precisely detect the features just like a human would. And as I said, we did all the testing, make sure that it works in large scale, make sure that it really works and it's precise enough. And now when we run the trains or run the cars at 60 miles per hour, you can imagine the LiDAR data is giving us 3D point cloud at 60 miles per hour with precise location of every point. We feed it to this GPU cluster with the deep learning model that we created in PyTorch. And what it does, we run the parallel inference on it and get detections from the model that says, okay, these are the points that I think they are crossing edges. These are the points that correspond to signals. These are the points that correspond to a traffic light and all that thing. And then we even programmatically took it to the next step. We had a database in Parquet that had all these old, already baseline features that, hey, this is in our outdated database where our features are. And we kind of married that up and compared it programmatically with this existing database. And there were two things that could happen. Either you found a nearby feature, so old database had it, deep learning model detected it too. And because the deep learning model was more precise enough, at that point, you could be done. You could say, okay, well, we detected it, we trust what deep learning says, and we can randomly check it if really need be. Or the second scenario that can happen is that nothing was found, meaning that, well, the deep learning model is telling you that there's a traffic light here, but in the old database, it says nothing is there within some vicinity, some radius. Well, an analyst can only go and look at that location and say yay or nay. So in that case, instead of an analyst having to go through the 200,000 features, now they're only going through the short list of features where there was discrepancy between the old database and the new database. A new database being created by the deep learning model. Here's the result of the model. You can see our average precision is 93.55%, and coupled by a recall of 90%, much higher than we wanted it to be. And the pretty interesting thing about it is that 94% of our detections had a sub-foot accuracy compared to what the human would pick. So if you had an analyst, you can go and click on a point versus the model telling you where that point is, you were within sub-foot of it in real world, which is way above and beyond the accuracy and precision that we needed for this purpose. And you can see on the left side, this is the concrete on the railroad crossing. So this is where the cars would basically go. This is part of the road. And you can see the edges of crossings. All those center points were detected perfectly by the model. And here's a switch mechanism that we talked about, how it could, help you go from one lane to another one. And you can see that one also was perfectly identified. So fast forward, what are we doing today? We're automating everything. Everything is automated from the LiDAR data collection at 60 miles per hour, going to the back office, going into the GPU cluster, running a parallel inference model, getting all of these detections out, and comparing it against our old database. That's what we're putting in place. And this way, no longer you need someone to go through 200,000 features by their computer. And this way, you also don't need to send someone physically on the ground to look at every single feature and be able to say, yeah, I got this location. Now I need to go and update it in the database. So you can see huge time saving, huge precision, and huge benefit to our operations, especially as we start thinking about the autonomous trains and things that rely on precise mapping. Well, with that, I will thank you for your time and take any questions within the next 2 minutes that we have left. Thanks, Tim. Yes, we are hiring. Absolutely, we are hiring. We actually have a few positions open on our websites. Definitely check out nscorp.com/careers or /jobs if I'm not mistaken. Definitely reach out if you have any recommendation. If you have anybody in mind, we always, of course, want a very good data scientist in our team. So Tim's asking, any projects to detect vehicles in crosswalks to avoid wrecks? To the best of my knowledge, that's something that our safety department is looking into. I do not have a whole lot of details on that. So Celia, if I'm pronouncing it correctly, is asking, how long did it take to create this deep learning model? Believe it or not, in less than 3 weeks, we had it all built. Our initial rollout, so the way we do it is that we create the first version of the model, and of course, incrementally, we run it large scale, get the false positives, get the true positives, and incrementally tune the model. The first version of the model that we created within 3 weeks had a precision recall about average of 82 to 3%. But of course, our business partners wanted to have it even higher and to reduce the workload on the analyst and what the analyst needs to look at. So we retrained the model within another 2 weeks, so a total of 5 weeks, if you will, and we got it to the acceptable result for the business partners, which is right now, I think it was, if I go back one slide, precision of 93.55 and recall of 90.45%. Another comment, that's insane. Expected it to be much longer. Yeah, that's partly because we've created a lot of automated modules for training new models. And so as soon as we get the labels, training the model and bringing it to a good precision recall is pretty fast. our believe it or not, our roadblock is always having that labeled set. And again, you can think about LiDAR 3D point cloud, very rich, 700,000 points per second, and you're talking about 19,000 miles of track. I mean, if you just do the calculations, we're talking billions and billions of points. So labeling a good, rich feature set, that was the long time consuming part of it. I'll take, I guess, one more question, and we can wrap this up so that everybody can use make use of the other sessions as well. Okay, looks like no questions. Well, I appreciate everybody for tuning in, and I hope you found it interesting. Definitely reach out to us. Again, norfolksouthern.com/jobs or /careers. And my LinkedIn profile is here too. If you all are interested in a position, or if you have anybody in mind, definitely please send them our way. I appreciate everybody and hope you all have a good morning. Thanks, guys.